Hi guys, welcome back to Data Every Day. Today we'll be looking at a data set of sales of summer clothes and has a lot of features, 43 different columns, and we'll be using all those features to try to predict the number of units sold for each sale. Alright, so let's hop right in. As you can see, I'm trying to make this video a little quicker today. I'm already importing everything here. We're going to use NumPy, Pandas, Matplotlib, and then we'll use a min-max scaler, label encoder, and that classic train test split function. And we'll be using TensorFlow to train a classifier for this data. So let's run that, and let's import the data using Pandas read CSV function. And we can get the file path right over here. This is the file we want. So copy file path, paste it in, and take a look. Alright, and you can see right away, well, it has this little dot dot dot, so it's not showing us all the columns. So why don't we go in the console and just type pandas.setOption max columns none. Enter. Now if we just look at this, we should get all the columns on here. And we have a good number of columns. It's 43 different columns, but as you can see, a lot of them are completely useless columns. Like product, picture, this stuff is not going to help us in trying to classify, although it may be useful to use this in some sort of exploratory data analysis, bringing up the pictures themselves against the sales. But we're going to drop those, and there's actually so many unnecessary columns here. I'm not even going to go through why we need to drop them. If you want, you can take a closer look at the data set. I'm just going to copy and paste in these columns, which I've collected, all the columns that we really don't need. And I was able to get a fairly decent accuracy without using any of these columns. I'm sure if we had more time, or if we really wanted to, we could process these columns into more useful features. For example, the tags column which I dropped, we could actually go through, collect up all the unique tags. So take all the tags and then create a new feature for each tag, and then each example would have ones in the spots for the columns in which it had that tag present. But we're not going to worry about that. We're just going to drop the tags column. We're going to drop a whole bunch of these. I just made this list called columns to drop. We'll specify that, and then we'll say data.drop columns to drop. And first axis for column axis, axis 1, and in place true. So we'll just drop that, take another look at our data. It's much better now. We still have 25 columns, but it's not nearly as cluttered. Alright, so let's check out the null values first. So I should probably, before we get started here, let me just make a markdown, pre-processing. And we're going to check out missing values now. So to check the missing values, we can do data.isNull. This will give us a matrix of spots where it will only say true if there is a null value there. So it doesn't look like we have any visible, but we're going to take the sum across all rows to give us the number of null values in each column. And you can see we only have 1, 2, 3, 4, 5, 6, 7 different null value columns. But because I want to do a little more processing on this data, we're actually going to come back to the null values, and first we're going to start with encoding. So why don't we do this? Why don't we take this missing values and just move this down, and then we're going to encode first. So the only guys, okay, why don't we take a look at the data types, right? Well, we can just look at it here. It looks like everything is in numerical form except this column, product color, this column, product variation size ID, and whoops, I think that's it. I'm pretty sure these are the only two columns we have to worry about encoding. We actually have a pretty nice data set here. It's all numeric data, so it should make our lives easy. So I specified a function in the last video which looks something like this, and I'll just run through what this is saying again. ordinal encoding is basically going to take a categorical feature that has some sort of specified order. So, for example, where is it? It's called product variation size ID. This column. Okay, let me just show you what this looks like. And actually, why don't we get the unique values of it? So, this is a feature that gives a size, right? And we actually have way too many unique values in here. Why don't we, instead of doing unique, we'll do value counts, which will give us the count of each one. And right here, I'm actually going to go pandas.setOption again, and we're going to, this time we'll specify max rows, because we want to see all of these. Now we can see all of them, and you can see a lot of these unique values are not being used, right? There's only one in the whole data set, but these ones at the top are pretty important, right? And you can see these are the typical sizes, going from extra small up to extra large. Basically, we can use these as new features, and the reason, we can use ordinal encoding on them, which, because they take on an order, right? It goes from extra small to extra large in a progressive order. We can just put them all into one feature column and just have the number increase as the size gets bigger. So this function I wrote is going to take an ordering of the columns we want, and it's going to basically ordinal encode that column, which means it'll take the index in the ordering and set the column value equal to that. So, for example, let's say we want to make a size ordering. Okay, I've already written it just to save time. I'll paste it in. But this is what we want, right? Extra small all the way to extra large, progressing through. So it starts small, it gets big. Now we can leave off this guy because there's only 6 examples. It's not really worth it. So let's say this is our ordering, and we're going to have to modify this function a little bit. Because there are so many other sizes that we don't want, we only want to encode it if it's in the ordering that we specified. So all we have to write at the end is if x in ordering. So that means x will be turned into its index in the ordering, in this ordering, right? Only if it's in the ordering already. And else, otherwise, we'll set x to be a null value. And so that will give us much cleaner data in this column. And so let's run that. Alright, let's set the column, which is called product variation. I gotta grab it up here. Product variation size ID is now going to be ordinal encode data, product variation size ID, and size ordering. And we'll run that. And now let's take a look at the number. Well, first of all, let's look at the column. And before I do that, I just want to set the rows option back to 20, because otherwise it'll load up our whole data set. We don't want that. So let's take a look at this. No. Wrong. This one. Alright. And now you can see everything has been converted into a number. Where before, let me see this. Before, medium, extra small, now we have 3, 1, 1. Because 3 is medium, 1 is extra small, 1 is extra small. See, so it's been encoded. And anything that wasn't one of these has become null. So now what we can do is we can change the nulls to be the mean, which is what we'll do for all of them, because that is, we have only one more categorical variable left. And so let's just work with that last one first. Okay, that was the product color. This one has colors and text, but we can use one-hot encoding to change this into a bunch of features, one for each color. And let's just see what the unique values in this. So that's quite a few different colors, but we can still use one-hot encoding here. So I've written this function a lot of times. This is my one-hot encoding function, which will take in the data and a column and create a dummies matrix, which, if you're not sure, pd.getDummies will take in, I'll use on the product column to show you, I'll take in some slice of the data frame, product color, and it will give back each unique value in that column as a new column, and the 1 means that example 3's value was black, and there's zeros in all the others. So example 0's value, can we find it? Where's a 1? It's got to be 1. Oh, here it is, white. So example 0's value is white, example 1's value, example 3's value is black. Let's check back up here to see if that's correct. Example 0's value is white, example 3's value was black. Good. So this thing is going to be our new set of features. We're going to concatenate it with the original data, and then we're going to drop the original column that this came from. And so we'll just specify that and then say data equals one-hot encode data, and the column we're specifying here is product color. Alright, so now we should have fully numeric data. And we can check that by just saying data.dtypes, data types, equals object. So this will return a matrix of all the object values for each column, rather a vector I should say, and then we can sum across that to get all the object values in the whole data frame, and 0. So we don't have any more strings to deal with. Everything is numbers, which is great, because now we can deal with missing values directly by imputing their means. So let's just take a look at the missing values again. So we'll get the isNull.sum, and we can see, okay, let's just bring back, how do I, what? We're going to do max columns. So I want to see all of these. Oh wait, it should have been max rows. Oh my. Okay. Alright, so looks good to me. 1, 2, 3, 4, 5, 6. So there's 6 different columns, and they're all numeric. And the way we're going to fill in all these null values is going to be with by imputing the means of each column. So let's make a list of all those columns. I just have it here, so to save time. I've written out each name that has null values, each column name that has null values, and we're just going to fill the null values for each of those columns. So for column in null columns, data subcolumn is going to be data subcolumn dot fill na, which means fill null values, with data subcolumn dot mean. So it's going to fill all these missing values with the mean of that respective column. Run that. Now if we take another look, this time we'll sum over both axes to get the total number of null values in the data frame, and we're down to 0. So now we have no more null values to worry about. Alright, we're on to scaling. So now we'll split our data between y and x, and y is going to be, let's see, what is y here? Y is going to be units sold, right? Can we check data? Let's just check data here. Oh no. I almost did it with this. Okay. This is very annoying. I have to keep changing it back and forth. No, not 20. Okay. What? Alright. Now we'll do this. And we can see. Okay. Units sold is going to be our Y. So, units sold. And our X will be everything except units sold. Not in place. Okay. So now we're going to scale our X. So we'll create a scalar object using the min-max scalar that we imported at the beginning. And X is going to be scalar.fitTransform X. So this will fit the scalar to our data, and then it will transform X into the scaled version. And min-max scalar just scales all the ranges between 0 and 1. And we will make it back into a data frame because it returns a NumPy array. And we'll specify that the columns should be as they were before. So now our X should look like fully scaled. Looks good. And our Y will be a vector of the units sold. Now, but do you notice something about this units sold? It's not continuous. These are actually discrete values. We take the unique. There's actually only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Did I count that right? I think there's 15 actually. 3, 6, 9. Yeah, 15. 15 unique values. So what that's saying is we probably shouldn't use regression. We should use classification. We should convert these into classes, and then we can use a classifier to try to get accuracy at classifying each sale into one of these. So let's say a little more encoding, and we'll make our encoder a sklearn label encoder, and this is great for your label column. We just say y equals encoder.fitTransform y. That's all we have to do. And to get a sense of what that's doing, we'll make mappings, which will be a dictionary that maps an index to a label for every index and label in enumerate encoder.classes. So the encoder will store the classes, these guys, and we'll just create an index that maps each new value to the old value. And we'll take a look at what y mappings looks like. And you can see 1 has been mapped to 0, all the way up to 100,000 has been mapped to 14. So we look at y now, it's just these values instead of these ones. That'll just make it easier for our model. Okay, so let's start training. So right here, last step before we train is just split xtrain xtest, ytrain ytest equals train test split xy, the train size of 80%. Alright, and now we'll start building our TensorFlow model. So we'll set it up with the input layer, will be a tf.keras.input. For the shape will be specified, we have to make sure the shape matches the number of features we have, which is, actually, let's just take a look at x. Uh, 124. So 124 long vector, and x will be tf.keras.layers.dense, which is a fully connected layer with 16 nodes and ArrayLu activation, as usual. This architecture works very well on tabular data. This is just that classic architecture. Alright, and then we do another dense layer, but this time we pass in x. And then our output layer will be another dense layer, but we will use the number of classes now. And there were 15 classes that we counted, right? So 15, one for each class that we're trying to classify. Here we have a softmax activation, and we pass in x. Now our model is going to be a tf.keras.model, specifying the inputs as inputs and the outputs as outputs. Okay, now we'll compile our model, model.compile, and we'll specify our optimizer, which will be atom, our loss function, which will be sparse categorical cross entropy, as we have multi-class problem, and our metrics will just be accuracy. Alright, then we'll specify the batch size and epochs. Batch size will be 32, and epochs will be, let's start with something big, 300. And then we'll fit our model. So model.fit, and we'll train it on the X train, Y train. We'll specify a validation split, and batch size will be our batch size that we specified, and our epochs the same. And then we'll just turn off verbose mode so it doesn't clutter the notebook. And let's store that in a history variable. Alright, so while that trains, it shouldn't take very long, but we can start plotting our results. So plot.figure, fig size 14 by 10, so a good size. And then we'll make an epochs range, which will just be the range from 1 to epochs plus 1. And that's simply because range will set it from 0 and not including the final value, so we just shift it over by 1. Then our train loss will just be our history object that we created here, right? Has a history attribute, which we index at loss to get our training loss. And we can do the same thing, except here validation loss, and this is val loss, right? And then we'll plot on the x-axis the epochs range, and on the y-axis the train loss, and label here training loss. And then here validation loss. Okay, plot.x label will be epoch, plot.y label will be loss, and the legend will be positioned in the upper right. And this is a little boring, but let's just get through this. Now we'll show. And this is how our model trained. So it's interesting. You see the training loss continues to go down. Oh, what happened here? What is this? Why is it showing U and P? Let me just see. PyPlot legend. Okay, you know what? I'm not sure why that's happening. Basically, the blue is training and the orange is validation. Let's go ahead now and figure out when does the validation loss start to go back up. Because at first the model's learning, right? But what happens is it starts to overfit. When this is going down constantly, the training loss is going down because we're memorizing the model. It's overfitting. It's getting too good at memorizing the training examples it's seen, and it's losing the ability to generalize to examples it hasn't seen, which is what the validation set is. So we have to find what's the minimum of this validation curve. When does it stop going down and start going up? And we can do that just using numpy.argmin of val loss. And it says epoch 60, right around here, is the minimum. This is when the validation loss was at its minimum. So what we'll do is just go back and change the epochs to 60, and we'll retrain our model only for 60 epochs this time. That took a very short time. But now if we look, you can see it is no longer going back up. Now we can evaluate our model on the test set to see how it does on completely new and unseen data. And we ended up with a accuracy of about 60%, which is pretty good. I think we can do a little better though. I think we can. Well, I feel like maybe we had a bad value for the minimum. Let's try training it on a few more epochs, which when I was messing around with this, I had something like 160. And let that train. And when that plots, we should get, it should still continue to go down, right? It's not really going up here. But now we'll probably have better accuracy. And yes, now we're up to 72%. So that's pretty good. I mean, considering the data set, I think this is a pretty good performance. So I think that concludes today's video. If you enjoyed it, make sure to subscribe and hit the bell, and leave a comment below with any suggestions. Thank you so much for watching. I'll see you guys tomorrow. Have a great day.